There is a question that has followed humanity for as long as we've been able to think beyond the next sunrise. It's not loud, it doesn't demand attention. It waits quietly, surfacing in moments of stillness, when the distractions fade and the night grows quiet. If the universe had a beginning, what came before it? At first, the question feels obvious, almost unavoidable. Everything you've ever known has a before. Before this moment, there was another. Before this planet existed, there was dust and gas. Before stars ignited, there was darkness. Cause follows cause. Beginning follows beginning. The chain stretches backward endlessly through time. And then we reach a point where the chain stops. 13.8 billion years ago, according to our best measurements, the universe began. Not just the matter within it, not just stars or galaxies or space itself. Time began. The very framework that allows one moment to follow another came into existence. This is where the question breaks. Because if time itself began with the universe, then the word before loses its meaning. Before requires time. It requires a sequence. Asking what came before the Big Bang may be like asking what lies north of the North Pole. The language survives, but the concept does not. And yet the question refuses to disappear. Our minds rebel against it. We are creatures shaped by cause and effect. When we see motion, we assume something set it in motion. When we see fire, we assume a spark. When we see an expanding universe, cooling and forming structure, we instinctively ask what triggered it. The discomfort comes from realizing that this instinct may no longer apply. If you could rewind cosmic history, you would see the universe growing hotter and denser. Galaxies rush together, stars dissolve back into gas, atoms fall apart, matter becomes a glowing plasma. Space itself shrinks. Rewind further, and even the particles lose their identities. Temperature and density climb beyond anything we can reproduce or observe. And then, at a point 13.8 billion years in the past, our equations fail. Not gradually, completely. They return infinities. This breakdown is what physicists call a singularity. Not a place we understand, but a signal that our understanding has reached its limit. General relativity, our best description of space-time and gravity, tells us the universe began in an infinitely dense state. But infinite values aren't physical answers. They're signs that the theory can no longer describe reality. Quantum mechanics, which governs the smallest scales, should help, but it doesn't. Gravity and quantum physics refuse to cooperate under these conditions. When we try to apply both at once, the mathematics collapses. We are left staring at a boundary beyond which our most successful theories cannot see. This is not a failure of science. It is the edge of it. Some physicists argue that the question itself is flawed. If time began with the universe, then there was no before to speak of. The Big Bang wasn't an event that happened in time, it was the event that created time. Others disagree. They suggest the Big Bang was not a true beginning, but a transition, a phase change, a moment where something older transformed into the universe we now observe. In these models, time may stretch backward indefinitely, even if our universe does not. There are ideas of bouncing universes, of cosmic cycles, of quantum fluctuations giving rise to space-time itself. There are proposals where our universe is one region among many, or where time behaves differently at the deepest level of reality. None of these ideas are proven. Some may never be testable, but they all arise from the same discomfort. The sense that a universe with an absolute beginning violates our deepest intuitions about cause, and existence. What makes this moment in history remarkable is how far we've already come. A few centuries ago, the origin of the universe belonged entirely to myth. Today, we can describe the universe fractions of a second after its birth. We can measure ancient radiations still echoing from that early era. We can reconstruct cosmic history with extraordinary precision. And yet the final step remains hidden. Why is there something rather than nothing? Why did time begin at all? And what does nothing even mean in a universe governed by quantum laws? These questions sit at the intersection of physics and philosophy. They challenge not just our equations, but the language we use to describe reality. They force us to reconsider whether nothing is truly empty, whether beginnings require causes, and whether time itself is fundamental or emergent. In asking what came before the Big Bang, we are not just asking about the universe. We are asking about the limits of human understanding, about whether reality is obligated to make sense to minds shaped by evolution on a small planet orbiting an ordinary star. To go further, we must first dismantle a misconception: the idea that nothing is simply empty space. Because, as we'll discover, empty space is anything but empty. And if the universe truly emerged from nothing, then that nothing may be the strangest thing of all. When you imagine nothing, what do you see? Perhaps a dark room with no furniture. Perhaps empty space stretching in all directions, silent and void. Perhaps you close your eyes and picture the absence of everything, a blank canvas where reality hasn't yet painted anything at all. This is how most of us think about nothing. It's the opposite of something. It's what's left when you remove everything that exists. But physics tells us a different story. According to our best understanding of how reality works, the kind of nothing you're imagining cannot exist. True emptiness, absolute void, perfect absence. These things are forbidden by the laws that govern the universe. Empty space, it turns out, is not empty at all. This revelation comes from quantum mechanics, the branch of physics that describes the behavior of the very small. At the quantum level, reality stops following the rules we're used to. Particles don't have definite positions until you measure them. Energy can appear and disappear in ways that seem impossible. And space itself, even when you remove every particle and every bit of light and every force you can think of, still contains something. We call it vacuum energy. Even in the emptiest region of space you could imagine, far from any stars or galaxies, far from any matter or radiation, there's a baseline energy that cannot be removed. It's built into the fabric of space itself. You could think of it as the universe's idle hum, the lowest note that reality can play. It never stops. It can't be turned off. This isn't just theoretical speculation. We've measured it. We've seen its effects. There's an experiment you can do, simple in concept though difficult in practice, that proves empty space has energy. Take two metal plates and place them very close together in a vacuum. Quantum mechanics predicts that the energy of empty space between the plates will be slightly less than the energy of empty space outside them. This difference creates a force that pushes the plates together. It's called the Casimir effect, and it's real. We've measured it. Empty space pushes on things. The reason this happens involves one of the strangest features of quantum mechanics. At tiny scales and short timescales, the universe is uncertain. There's a principle discovered by Werner Heisenberg that says you can't know everything about a particle at once. The more precisely you know its position, the less precisely you can know its momentum. The more precisely you know its energy, the less precisely you can know when it has that energy. This uncertainty has consequences. It means that even in empty space, particle and antiparticle pairs can pop into existence for brief moments before annihilating each other and disappearing. These are called virtual particles. They're not quite real in the way a normal particle is real, but they're not quite imaginary either. They exist for such short times that they don't violate the law of energy conservation. They borrow energy from the uncertainty itself, then pay it back before the universe notices, so to speak. This happens everywhere, constantly. Right now, as you listen to these words, the space around you is seething with quantum activity. Particles flash in and out of existence. The electromagnetic field fluctuates. The fabric of space itself trembles with microscopic vibrations. You can't see it or feel it because these fluctuations are incredibly tiny and incredibly brief. But they're there. They're measurable. They affect how particles behave and how forces work. So when we talk about the universe coming from nothing, we need to be careful about what we mean. If we mean the kind of nothing that includes quantum vacuum energy and virtual particles, and the fundamental uncertainty of reality, then perhaps that's not so mysterious after all. That kind of nothing naturally gives rise to something. It's restless. It's dynamic. It contains the seeds of creation. But that raises another question. Where did that quantum vacuum come from? Where did the laws that govern it come from? If we say the universe emerged from quantum nothingness, we're really saying it emerged from a particular kind of something, something with structure and rules and properties. We've pushed the question back a step, but we haven't answered it. Some physicists argue that we need to think about an even deeper kind of nothing. Not just empty space in our universe, but the absence of space itself. The absence of time. The absence of physical law. A state, if you can call it that, where not even quantum mechanics exists. Where there are no fields, no particles, no dimensions, no properties at all. Pure, absolute nothingness. But here we run into a problem. How do you describe something that has no properties? How do you apply mathematics to it? How do you even think about it? Our physics is built on the idea that things have properties, that causes lead to effects, that time flows and space extends. When you remove all of that, you're not just removing the contents of the universe. You're removing the framework we use to understand anything. Maybe that's the point. Maybe when we ask what came before the Big Bang, we're asking a question that assumes time works the way we think it does. We're assuming there was a before. We're assuming causation applies. We're assuming the universe is something that was created rather than something that simply is. These assumptions feel natural to us, but they might not reflect how reality actually works at its deepest level. The quantum vacuum, with all its energy and uncertainty and virtual particles, might be the closest thing to nothing that can exist. It might be the ground state of reality, the baseline from which everything else emerges. It's not the comfortable, intuitive nothing of empty space. It's stranger than that. It's active. It's pregnant with possibility. And this brings us to the Big Bang itself. If empty space seethes with quantum activity, if uncertainty allows particles to appear from nothing, if the vacuum has energy built into its very structure, then perhaps the Big Bang wasn't an explosion from absolute void. Perhaps it was something else entirely. A transition, a transformation, an expansion of something that already existed in a form we can barely describe. To understand what that means, we need to look carefully at what the Big Bang actually was. The Big Bang is probably the most misunderstood event in science. The name itself misleads us. It suggests an explosion, something bursting outward into empty space with a tremendous bang. You might picture it like a firework going off in the darkness, matter flying in all directions from a central point. But that's not what happened. The Big Bang wasn't an explosion in space. It was an explosion of space itself. Imagine the entire universe, everything that exists, compressed into a region smaller than an atom. Not just matter and energy, but space itself. There was no outside. There was no container. There was no void waiting to be filled. Space and time and energy were all concentrated in this incredibly dense state, and then they began to expand. Not into anything, because there was no anything to expand into. Space created more space as it grew. This is difficult to visualize because we have no experience with anything like it. Every explosion you've ever seen happens in space that already exists. A bomb goes off and matter rushes outward through the air. A star explodes and its material spreads into the surrounding cosmos. But the Big Bang was different. It wasn't happening in space, it was happening to space. We can trace this expansion backward in time with remarkable precision. We know the universe is 13.8 billion years old. We can describe what it was like when it was just a few minutes old, when it was hot enough that atomic nuclei were forming. We can go back further to when it was just seconds old, when even protons and neutrons couldn't exist, and matter was a soup of fundamental particles. We can go back to tiny fractions of a second after the beginning, but there's a limit. At a certain point, our physics breaks down. We call this the Planck epoch, the earliest moment we can meaningfully describe. It lasted an incomprehensibly brief instant, far shorter than any time we have direct experience with. Before that moment, or at that moment, the universe was so hot and dense that our equations stop working. General relativity, which describes gravity and the large-scale structure of space-time, conflicts with quantum mechanics, which describes the behavior of particles and forces. We don't yet have a theory that unifies them. So when we talk about the Big Bang, we're really talking about what happened after that first incomprehensible instant. We're describing the expansion and cooling of the universe from a state we can model, even if we can't yet describe the very beginning itself. The singularity, the point of infinite density that our equations suggest, might not be real. It might be a sign that our mathematics is incomplete, that we're trying to use tools that weren't designed for such extreme conditions. What we do know, with great confidence, is that the universe was once incredibly hot, incredibly dense, and incredibly small. And then it expanded. In the earliest moments of this expansion, something remarkable happened. The universe didn't just grow steadily, it inflated. For a fraction of a second, space expanded exponentially, doubling in size again and again at an almost unimaginable rate. This is called cosmic inflation, and it left its fingerprints on everything we see. Inflation explains several features of the universe that would otherwise be puzzling. It explains why the universe looks roughly the same in all directions. Without inflation, different regions of space would have started so far apart that they could never have influenced each other. Yet they somehow ended up with the same temperature and density. Inflation solves this by saying they were once close together, in contact, before being stretched apart faster than light could travel between them. It also explains why the universe is so flat. Space could curve in on itself like the surface of a sphere, or curve outward like a saddle. But measurements show that it's geometrically flat, at least as far as we can measure. Inflation stretched space so much that any curvature it might have had became undetectable, like how the surface of the Earth looks flat when you're standing on it, even though the planet is round. The evidence for this history is all around us. There's the cosmic microwave background radiation, a faint glow filling all of space. It's the cooled remnant of the intense heat from the early universe, stretched by expansion into microwave wavelengths. We've mapped its tiny variations in temperature, and those variations match exactly what inflation predicts. They're the seeds from which galaxies grew, quantum fluctuations stretched to cosmic scales. There's the motion of galaxies themselves. When we measure their light, we find it shifted toward the red end of the spectrum. This redshift tells us they're moving away from us, and the farther away they are, the faster they're receding. This is exactly what you'd expect in an expanding universe. Space itself is stretching, carrying galaxies along with it like raisins in rising bread dough. There's the abundance of elements. In the first few minutes after the Big Bang, when the universe was still hot enough for nuclear reactions, hydrogen fused into helium and trace amounts of other light elements. We can calculate how much of each element should have formed, and when we look at the oldest stars and gas clouds, that's exactly what we find. The universe remembers its early moments in the proportions of atoms it contains. All of this evidence points to the same conclusion. The universe had a beginning. It was once far smaller, far hotter, far denser than it is now. It expanded and cooled, and that expansion continues today. This isn't speculation. It's not just one theory among many. It's the foundation of modern cosmology, tested and confirmed in countless ways. But notice what the Big Bang theory describes. It tells us how the universe evolved. It tells us what happened as space expanded and matter formed and stars ignited. It traces cosmic history with beautiful precision. What it doesn't tell us is why that hot, dense state existed in the first place. It doesn't explain what set the expansion in motion. It doesn't answer the question we started with. The Big Bang describes the transformation of the universe from one state to another, but it doesn't explain the origin of that initial state. For that, we need to look deeper into the nature of reality itself, into the quantum realm where particles appear from nothing and energy fluctuates in the void. We need to ask whether the universe itself could be a quantum phenomenon. In the quantum world, impossible things happen all the time. Particles appear where they shouldn't be. They tunnel through barriers they don't have enough energy to cross. They exist in multiple states at once until someone observes them. The rules that govern everyday objects, the rules that feel solid and dependable, simply don't apply at the smallest scales. And this might be the key to understanding how a universe can begin. There's a phenomenon called quantum tunneling that defies common sense. Imagine rolling a ball toward a hill. If the ball doesn't have enough energy to reach the top, it rolls back down. It can't simply appear on the other side. That's how classical physics works. But in quantum mechanics, there's a probability, usually very small, that a particle can tunnel through the barrier and emerge on the other side without ever having enough energy to climb over it. It's not that the particle goes around or digs through. It simply appears on the far side, as if the barrier wasn't there. This happens because particles at the quantum level aren't really particles in the way we usually think of them. They're wave functions, probability clouds, distributions of likelihood spread across space. And wave functions can extend through barriers, giving particles a chance to materialize where they shouldn't be able to reach. We've measured this. We've built technologies that rely on it. It's not speculation. It's how reality works when you look closely enough. Now apply this thinking to the universe itself. What if the Big Bang was a kind of quantum tunneling event? What if the universe didn't need a cause in the traditional sense because it tunneled into existence from a state where existence wasn't yet defined? This isn't as far-fetched as it sounds. Several physicists have proposed models along these lines, and while they're highly speculative, they're grounded in the mathematics of quantum mechanics and general relativity. One way to think about it involves energy. In classical physics, you can't create something from nothing because energy is conserved. You can't get more energy than you started with. But the universe might be special. When you account for gravity, the total energy of the universe could be zero. The positive energy of matter and radiation might be exactly balanced by the negative energy of gravity. Mass attracts mass, and that attraction represents a kind of negative energy, a debt in the cosmic ledger. If this is true, then creating a universe doesn't require any energy at all. It's like writing a check and depositing it in your own account. The numbers change, but the total stays the same. A universe with zero total energy could emerge from quantum fluctuations without violating conservation laws. It would be a fluctuation that grew, a borrowed energy that never needs to be paid back, because the books already balance. Alexander Vilenkin, a cosmologist who has thought deeply about these questions, proposed that the universe could have tunneled from literally nothing into the something we observe. Not from a quantum vacuum with its seething energy, but from a state with no space, no time, no properties at all. His mathematics suggests that such a transition is possible, that quantum mechanics allows for it. The universe would be self-creating, popping into existence through the same kind of process that allows particles to tunnel through barriers. Another approach comes from Stephen Hawking and James Hartle. They suggested that the universe has no boundary, no beginning in the traditional sense. Using a mathematical trick involving what they called imaginary time, they described the universe as a self-contained entity, smooth and finite, but without an edge or a starting point. It's like asking what's north of the North Pole. The question assumes something that isn't there. In their model, asking what came before the Big Bang is similar. Time itself is part of the universe, and the universe simply is, without requiring a moment of creation. These ideas push at the edges of what we can test. We can't create universes in laboratories to see if they tunnel into existence. We can't observe the moment of cosmic birth directly. We're working with mathematics and logic, trying to extend our theories into realms where we have no data. But that doesn't make these ideas meaningless. They're attempts to take what we know about quantum mechanics and apply it consistently to the biggest question we can ask. The key insight is that quantum mechanics doesn't just describe particles. It describes fields, forces, even space-time itself. If everything else in the universe follows quantum rules, why should the universe as a whole be exempt? If particles can appear from quantum fluctuations, if virtual particles can borrow energy for brief instants, if uncertainty is woven into the fabric of reality, then perhaps a universe can begin through the same mechanisms. There's a certain elegance to this. It means the universe doesn't need an external cause. It doesn't require something outside of physics to set it in motion. The laws of quantum mechanics, combined with gravity, might be sufficient to allow a universe to create itself. Not through magic, not through violation of physical law, but through processes we already know exist at smaller scales. But this elegance comes with questions. If the universe can tunnel into existence, why did it happen? Why this universe with these properties? If quantum mechanics allows for such creation, does it happen once or many times? And perhaps most fundamentally, where do the laws of quantum mechanics come from? We're explaining the universe's origin by appealing to quantum mechanics, but quantum mechanics itself is part of reality. It requires space and time and mathematical structure to be meaningful. Some physicists have taken this line of thinking even further. If quantum tunneling can create one universe, perhaps it creates many. Perhaps the process that gave birth to our cosmos is ongoing, happening again and again in ways we can't observe. Perhaps we're just one bubble in an endless foam of creation, one possibility among countless others. This idea, the multiverse, offers another perspective on cosmic origins. But it also raises new questions about what it means for something to exist. The idea sounds like science fiction at first. Multiple universes, perhaps infinitely many, each with its own laws and constants and history. Parallel realities where things happen differently, or where the rules of physics themselves are different. It seems extravagant, unnecessary, too strange to take seriously. And yet some of our best theories point in exactly this direction. It starts with cosmic inflation, that brief period of exponential expansion in the earliest moments of our universe. Inflation explains why our universe looks the way it does, why it's so uniform, why it's geometrically flat. The theory works beautifully to account for what we observe. But when you work through the mathematics carefully, something interesting happens. Inflation doesn't want to stop everywhere at once. Think of it this way. Inflation is driven by a field similar to an electromagnetic field, but different, pervading all of space. This field has energy, and that energy drives the expansion. Eventually, the field decays, the energy converts into particles and radiation, and inflation ends. That's what happened in our region of space 13.8 billion years ago. But quantum fluctuations affect this field, just like they affect everything else at small scales. In some regions, the field might decay a bit earlier, in others, a bit later. And in some regions, it might not decay at all. Where inflation continues, space keeps expanding exponentially. It doubles and doubles again, creating more volume. Within that expanding space, more quantum fluctuations occur, creating more regions where inflation might end and others where it continues. The process becomes eternal. Inflation stops in some places, creating bubble universes like ours, but continues elsewhere, creating more space where more bubbles can form. It's a fractal process, unending, producing an infinite number of pocket universes within an ever-inflating background. This is called eternal inflation, and it's not fringe physics. It emerges naturally from our best models of how inflation works. You don't have to add anything exotic or speculative. You just follow the mathematics where it leads, taking quantum mechanics seriously, and this is what you get. A multiverse of bubble universes, each beginning with its own Big Bang, each potentially having its own properties. And here's where it gets even stranger. Those properties might not be the same everywhere. In our universe, the electron has a certain mass, the speed of light has a certain value, gravity has a certain strength. These numbers seem arbitrary. There's nothing in our current theories that explains why they have the values they do, rather than some other values. We measure them, we plug them into our equations, and we discover that they work together to create a universe where complexity can emerge, where stars shine and planets form and life becomes possible. But they could have been different. Change the strength of gravity slightly, and stars burn too fast or too slow. Change the mass of electrons and atoms don't form properly. Change the values enough, and you get a universe that's just hydrogen forever, or one that collapses immediately, or one where matter never clumps together. The range of values that allows for interesting universes appears to be narrow. We call this fine-tuning, and it's puzzled physicists for decades. The multiverse offers an answer. If there are countless universes with different properties, then some will have the right conditions for complexity and some won't. We find ourselves in one of the ones that works because we couldn't exist in the ones that don't. It's called the anthropic principle. We observe a universe suited for observers because unsuitable universes have no one to observe them. This isn't just philosophical musing. String theory, one of the leading candidates for a theory of quantum gravity, suggests something similar. String theory requires extra dimensions beyond the three of space and one of time that we experience. These extra dimensions are curled up, compactified into shapes too small to detect. But there are many ways to curl them up, an enormous number of possible configurations. Each configuration gives rise to different physical laws and constants. The number of possibilities is staggering, far more than you could ever explore by counting. Each one represents a different possible universe, a different set of rules. If eternal inflation produces bubble universes and string theory provides different possible laws for those bubbles, then you have a mechanism for actualizing all those possibilities. The multiverse becomes not just possible, but perhaps inevitable. Of course, this raises an obvious question. If we can't observe these other universes, if they're forever beyond our reach, separated from us by inflating space, are they really science? Science is supposed to be testable. We're supposed to make predictions, do experiments, compare results with theory. How do you test a theory that predicts things you can never see? It's a fair criticism, and physicists debate it vigorously. Some argue that the multiverse is a consequence of theories we can test. We test inflation by looking at the cosmic microwave background. We test quantum mechanics by doing experiments here on Earth. If those theories lead logically to a multiverse, then the multiverse is as real as the theories that predict it. Others worry that we're slipping into metaphysics, that we're abandoning the empirical foundation that makes science reliable. There's also a deeper concern. If anything that can happen does happen somewhere in the multiverse, does that explain anything at all? If our universe is one of infinitely many, chosen not by design or necessity, but by random chance, have we really answered the question of why things are the way they are? Or have we just given up on finding a deeper explanation? The multiverse might tell us that our Big Bang was one event among many. It might place our cosmic origin in a larger context. But it doesn't answer the fundamental question. It just pushes it back. If there's a multiverse, what started it? If eternal inflation creates bubble universes endlessly, what started the inflation? If quantum mechanics allows universes to tunnel into existence, where did quantum mechanics come from? Perhaps the answer lies not in asking what happened before, but in questioning whether before even makes sense. Perhaps time itself doesn't work the way we think it does. Perhaps our intuitions about causation and sequence break down when we apply them to the universe as a whole. To understand cosmic origins, we might need to understand time itself. We experience time as a river, flowing in one direction, carrying us from past through present toward future. Events happen in sequence. Causes precede effects. Yesterday came before today, and today will come before tomorrow. This seems so fundamental, so obvious, that questioning it feels absurd. But when we ask what came before the Big Bang, we're assuming that time extends backward beyond it. And that assumption might be wrong. Einstein taught us that time isn't what we thought it was. Before relativity, we imagined time as universal, the same for everyone, everywhere. A cosmic clock ticking at the same rate throughout the universe. But Einstein showed that time is flexible, relative. woven together with space into a four-dimensional fabric we call space-time. Time passes at different rates depending on how fast you're moving and how strong the gravity is where you are. An astronaut orbiting Earth ages slightly slower than someone on the ground. Time near a black hole flows more slowly than time far away. These aren't illusions or measurement errors, they're real differences in how time passes. The universe doesn't have a single universal now that everyone shares. Events that are simultaneous for one observer happen at different times for another observer, moving relative to them. If time is part of space-time and space-time began with the Big Bang, then time itself began with the Big Bang. There was no before. The question, what came before, assumes time existed independently, waiting for the universe to start within it. But that's not how it works. Time is part of the universe. It emerged together with space and matter and energy. Asking what happened before time began is like asking what's north of the North Pole. The question uses words that make sense individually, but combine into something meaningless. This isn't just wordplay. It has real implications for how we think about cosmic origins. If time had a beginning, then the universe doesn't need a temporal cause. It doesn't need something that came before it to set it in motion. The entire concept of causation, which assumes time flows from cause to effect, might not apply to the universe as a whole. Some physicists take this even further. They suggest that time isn't fundamental at all, it's emergent, arising from something deeper. Carlo Rovelli, an Italian theoretical physicist, has developed a view of quantum mechanics where time doesn't exist at the most basic level. Instead, reality consists of events and relationships between events. What we experience as time is a kind of bookkeeping, a way of organizing how things relate to each other. But at the deepest level, there's no universal time ticking away. There's no absolute sequence. This sounds strange, but it solves certain problems in physics. When you try to combine quantum mechanics with general relativity, time becomes problematic. The two theories treat it differently. Quantum mechanics assumes a universal time parameter. General relativity says time is flexible and relative. At the quantum scale, near the Big Bang, these differences become impossible to ignore. Perhaps the solution is that time isn't fundamental. It's something that emerges when you have enough particles and events to define what we mean by change. Stephen Hawking explored another angle. He used a mathematical technique involving what he called imaginary time. In ordinary mathematics, numbers can be real or imaginary. Imaginary numbers involve the square root of -1, which sounds impossible but proves incredibly useful in physics. Hawking showed that if you treat time as an imaginary number in certain equations, the beginning of the universe becomes smooth. There's no singularity, no infinite density, no moment where the equations break down. In this framework, the universe has no boundary in time. It's finite but unbounded, like the surface of a sphere. You can travel across the surface of Earth in any direction and never reach an edge, yet the surface is finite. Similarly, you could travel through the universe's history in any direction and never reach a moment that counts as the absolute beginning. Time would blend into space near the Big Bang. The distinction between them would blur. The universe would simply exist, complete and self-contained, without requiring a moment of creation. These ideas are difficult to visualize because our brains evolved to navigate a world where time flows steadily forward. We remember the past, we experience the present, we anticipate the future. This structure feels built into reality itself. but it might just be built into how we perceive reality. At the quantum level, at the cosmic level, things might work differently. There's another perspective worth considering. Some physicists argue that time is an illusion arising from the second law of thermodynamics. Entropy, the measure or disorder, increases over time. Eggs break but don't unbreak. Coffee cools but doesn't spontaneously heat up. This arrow of time, this asymmetry between past and future, gives us our sense that time flows. But the fundamental laws of physics don't distinguish between forward and backward in time. They work the same way either direction. If time's arrow comes from entropy, and entropy is just a statistical property of systems with many particles, then maybe time itself is just a feature of our limited perspective. Maybe the universe, viewed from outside or from a timeless perspective, just is. All moments exist equally. Past, present, and future are all laid out in a four-dimensional block, and our consciousness simply moves through it, creating the illusion of flow. This is called the block universe, and it has both supporters and critics among physicists. If it's correct, then the Big Bang isn't an event that happened and then stopped happening. It's a region of space-time that exists timelessly. The universe doesn't evolve from past to future. It simply is, all at once, a complete four-dimensional structure. These perspectives challenge our deepest assumptions about reality. They suggest that when we ask what started the Big Bang, we might be asking the wrong kind of question. We're assuming time works universally, that causation applies everywhere, that there was a before waiting for an after. But if time began with the universe, or if time isn't fundamental, or if time is just a feature of how we perceive a timeless reality, then the question dissolves. Yet even these radical rethinkings don't fully satisfy. They explain or try to explain how the universe can exist without needing a temporal cause. But they leave another question untouched. The universe operates according to laws. Quantum mechanics, relativity, thermodynamics, these aren't arbitrary, they're precise, mathematical, elegant. Where do those laws come from? Why do they have the form they do? Whether time is real or emergent, whether the universe has a beginning or is timelessly complete, it still follows rules. And those rules themselves seem to require explanation. There's something remarkable about the laws of physics. They're written in mathematics, and the mathematics works. When you calculate where a planet will be next month using Newton's laws, it's there. When you predict how particles will behave in a collider using quantum field theory, they behave that way. The universe seems to follow precise mathematical rules, and those rules hold everywhere we can observe, from the smallest scales to the largest. This is strange when you think about it. Mathematics is something humans invented or discovered, depending on your philosophy. It's a language of patterns and relationships. Yet this language describes reality with uncanny accuracy. The physicist Eugene Wigner called it the unreasonable effectiveness of mathematics in the natural sciences. Why should abstract equations manipulated on paper or in computers tell us what actually happens in the physical world? One answer is that mathematics isn't just a description we invented, it's the underlying structure of reality itself. The universe doesn't follow mathematical laws. It is mathematical. Space and time, particles and forces. These are mathematical objects, patterns, relationships playing out according to logical necessity. In this view, physics doesn't just use mathematics as a tool. Physics is applied mathematics. Reality is mathematical structure made manifest. Max Tegmark, a cosmologist at MIT, has pushed this idea to its logical conclusion. He proposes what he calls the mathematical universe hypothesis. If the universe is fundamentally mathematical, and if all mathematical structures exist in some sense, then every possible universe described by self-consistent mathematics exists. Our universe is just one mathematical structure among infinitely many. We experience this one because we're part of its structure, embedded in its equations. This sounds wild, but it has a certain elegance. It means the laws of physics don't need an external explanation. They exist because they're mathematically consistent, and all mathematically consistent structures exist. The question isn't why these laws rather than others. It's why we find ourselves in a universe with these particular laws, and the answer is anthropic. We're here because these laws allow structures complex enough to wonder about laws. But this doesn't satisfy everyone. Even if mathematical structures exist necessarily, why should any of them be physical? What makes certain equations not just abstractions, but descriptions of real things? What's the difference between a mathematical universe that exists and one that's just a possibility, a pattern that could be written down but isn't instantiated anywhere? John Wheeler, a physicist who mentored many of the people working on these questions, suggested a different approach. He proposed that reality emerges from information, from bits of yes or no, from questions and answers. His slogan was, "It from bit," the idea that physical existence derives from information-theoretic existence. The universe isn't made of matter or energy or space-time. It's made of information, and everything else emerges from that. This connects to quantum mechanics in interesting ways. In quantum theory, measurement is fundamental. You can't separate the observer from what's observed. Reality doesn't have definite properties until something measures it, until information is extracted. Wheeler suggested taking this seriously. Perhaps reality is constructed from measurements, from the accumulation of bits of information. The universe computes itself into existence, in a sense, through an endless process of asking and answering questions. These are attempts to explain why the laws have the form they do. But there's another approach. Perhaps the laws are simply brute facts, not requiring further explanation. Perhaps asking why these laws is like asking why 2 + 2 = 4. It's not that something made it that way. It's that way because it couldn't be any other way. The laws are logically necessary, self-evident once you understand them properly. This is harder to maintain when you look at the specific details. The strength of gravity, the mass of the electron, the speed of light, these don't feel logically necessary. They're measured values. We can imagine them being different. There's no obvious contradiction in a universe where they have different values. So if they're not necessary, why these values? The multiverse provides one answer. If all possible values are realized somewhere, then we shouldn't be surprised to find ourselves where the values permit observers. But even the multiverse assumes certain laws hold universally. Quantum mechanics, the existence of fields, the structure of space-time, these provide the framework within which different universes can vary. Why that framework? Some physicists hope for a final theory, a theory of everything, that would show all the laws following necessarily from a single, elegant principle. String theory is the most developed candidate, attempting to unify all forces and particles into vibrations of tiny strings in higher dimensional space. If string theory is correct and unique, if there's only one mathematically consistent way to construct such a theory, then perhaps the laws of physics are necessary after all. They're the only way reality could be. But string theory hasn't achieved this yet. It has many versions, many ways the extra dimensions could be arranged, many possible vacuum states. It hasn't delivered the unique, inevitable theory that would make the laws self-explanatory. And some physicists doubt it ever will. Perhaps there is no final theory. Perhaps reality is more complicated than that, resisting reduction to a single, elegant equation. There's also the question of whether explanation can ever be complete. When you explain something, you explain it in terms of something else. You explain chemistry in terms of physics, biology in terms of chemistry, psychology in terms of biology. But eventually, you reach the bottom. You reach the most fundamental laws, whatever they are. And those laws can't be explained in terms of anything more fundamental, because there isn't anything more fundamental. They're the ground floor of explanation. Does that mean they're unexplained? Or does it mean they explain themselves somehow? Or does it mean we've reached the limits of what explanation can do? Different philosophers and physicists give different answers. Some are comfortable with brute facts, with laws that simply are. Others keep searching for deeper principles, hoping that understanding will extend further than we currently imagine. What's clear is that asking what started the Big Bang leads us here, to questions about the nature of law and existence itself. We've moved from a question about temporal causation, about what came before, to questions about logical necessity and mathematical structure and the ground of being. We're no longer asking what happened in time. We're asking why there's something rather than nothing, why that something follows rules, and whether those rules could be otherwise. These are questions that blur the boundary between physics and philosophy. They push science to its limits, and they remind us that for all we've learned, for all the precision of our theories and the success of our predictions, we're still creatures of limited understanding, standing at the edge of an infinite mystery, trying to make sense of our existence. We began with a simple question. If there was nothing, what started the Big Bang? We've traveled through quantum mechanics and cosmic inflation, through the nature of time and the origin of physical law. We've considered multiverse theories and mathematical structures and the limits of explanation itself. And we still don't have a complete answer. Perhaps we never will. This might feel disappointing at first. We've accumulated so much knowledge over the past few centuries. We've traced cosmic history back to fractions of a second after the beginning. We've mapped the universe on the largest scales and probed matter on the smallest. We've discovered that space expands, that time is relative, that empty space seethes with quantum activity. We've learned remarkable things, and yet the deepest question remains open. But there's another way to see this. The fact that we can ask such a question, that we can explore it scientifically, that we can narrow down possibilities and eliminate wrong answers, this itself is extraordinary. For most of human history, questions about cosmic origins belonged entirely to mythology and theology. People told stories, beautiful and meaningful stories, but they had no way to test them against reality. No way to check if they were right. That changed. We developed methods. We built instruments. We learned to observe carefully and think clearly and follow evidence wherever it led. We discovered that the universe has a history, that it follows laws we can understand, that its story is written in light and gravity and the behavior of atoms. We went from complete ignorance to detailed knowledge in just a few hundred years. That progress is astonishing, and the journey continues. Right now, physicists are working on theories of quantum gravity, trying to unite the very small with the very large. They're analyzing data from the cosmic microwave background, looking for patterns that might reveal what happened in the first moments of inflation. They're designing experiments to test the predictions of string theory and other approaches. They're pushing at the boundaries of knowledge, trying to see a little further. We may discover more, Perhaps we'll find evidence for the multiverse, some signature in the structure of space-time, or the distribution of galaxies that tells us we're one universe among many. Perhaps we'll develop a theory that explains why the laws of physics have the form they do. Perhaps we'll find that the universe is self-explanatory, that its existence requires no external cause because it's logically necessary. Or perhaps we'll find that some questions lie beyond the reach of science, that there are mysteries we can approach but never fully resolve. Either way, the exploration matters. The search for understanding is part of what makes us human. We're creatures who look up at the stars and wonder where we came from, who examine the structure of matter and ask what it's made of, who contemplate existence itself and try to make sense of it. This impulse to understand, to question, to push beyond what we currently know, this is woven into who we are. There's something profound about our situation. We're made of atoms forged in stars that lived and died billions of years ago. The carbon in our bodies, the oxygen we breathe, the iron in our blood. These elements were created in stellar furnaces and scattered across space by supernova. We're literally made of stardust, assembled by billions of years of cosmic and biological evolution into patterns capable of consciousness. And now those patterns, these temporary arrangements of stardust, can look back at the universe and try to understand their own origins. We're the universe examining itself, asking questions about itself, wondering where it came from. There's a kind of poetry in that, a strange loop, an unexpected recursion. The cosmos didn't just produce matter and energy and galaxies. It produced observers, questioners, beings who care about truth. We exist because the universe has very specific properties. The strength of gravity, the mass of fundamental particles, the way forces interact. These had to fall within narrow ranges to allow stars to form and planets to exist and life to emerge. We live in a universe that permits complexity. Change the laws slightly, and none of this works. No stars, no planets, no chemistry, no evolution, no us. Whether this is coincidence, or selection from a multiverse, or something else entirely, we don't yet know. But it grounds our inquiry in something personal. We're not just asking abstract questions about cosmic origins. We're asking about our own origins, about why we're here, about what had to be true for us to exist at all. Living with mystery isn't comfortable. We want answers. We want certainty. We want to know that we've figured it out, that we understand how things really are. But the universe doesn't owe us that comfort. It is what it is, and our job is to observe carefully, think clearly, and accept what we find even when it's strange or incomplete or unsatisfying. The question of what started the Big Bang may not have a single, clean answer. It may require rethinking what we mean by causation and time and existence. It may force us to accept that some aspects of reality are brute facts, not explicable in terms of anything deeper. Or it may surprise us with an answer we haven't imagined yet, some insight that makes everything click into place in ways we can't currently foresee. What we can say with confidence is that the universe began in a state we call the Big Bang, that it expanded and cooled, that it evolved according to physical laws we've partially uncovered. We can say that nothing is stranger than we thought, that quantum mechanics allows remarkable things, that our intuitions about time and causation may not apply at cosmic scales. We can say that we're part of this cosmos, intimately connected to its history, made possible by its properties. And we can say that the search continues. Each generation adds to what we know, refines our questions, pushes understanding a little further. The mystery remains, but it's a smaller mystery than it was, more precisely defined, closer to resolution, even if resolution remains out of reach. So perhaps the answer to our opening question isn't a single fact or theory. Perhaps it's a process, an ongoing exploration, a journey that matters more than the destination. We look up at the night sky, the same stars that have watched over humanity for thousands of generations, but we see them differently now. We know what they are, how they formed, what they're made of. We know they're part of a universe billions of years old, a universe that began in ways we're still working to understand. The darkness between those stars isn't empty. It's space itself, expanding, carrying galaxies away from each other, seeded with quantum fluctuations, pervaded by fields and energy and the echoes of ancient light. And somewhere in that darkness, among billions of galaxies, each containing billions of stars, we exist. Temporary, fragile, aware, asking questions, seeking answers, living with wonder.